So thanks for giving me the opportunity again to talk about LEGA-C, which is a survey of redshift 0.6 to 1 galaxies. And the singular goal of the survey is to access the stellar population and stellar kinematics information at this large look-back time. That hasn't been done before on this scale simply because it's really observationally expensive. We spend 1,000 hours observing with the VLT to get these data. And that begs the question, why? Because redshift 1 is not exactly high redshift these days. Why should we put so much effort into that? For that purpose, let me show this star formation history diagram in a different way than you're used to. Normally, we talk a lot about this high redshift end, about cosmic dawn at reionization, and then the peak at redshift 2 and 3. But if I take this analytical fit to all these data points that Maddow and Dickinson made, and I take the integral of that functional form, and I plot it a little bit differently, I get this. So here's the age of the universe, and here's the fraction of stars that the universe will ever form. I've extrapolated to the future, just along this power line. I keep going down. Let's assume that's true. What we then see is that by redshift 0, the universe is basically done forming stars and galaxies, right? And the other thing you notice is that there's a lot of growth, a lot of galaxy formation and assembly going on at these very moderate redshifts around redshift 1. And in fact, in this curve, the median formation redshift of all stars is just 1.2. And half of the stars form in the redshift range 0.6 to 2. Right? So all this very high redshift business is very exciting, but it has no relevance whatsoever on the assembly of the galaxies we see around us today. It's a galaxy formation story that's fascinating and exciting here. But if you want to know about galaxy assembly and how the stellar population is formed, you need to look in this redshift regime. So what we do with LEGA-C is we bring the archaeological approach that we usually have at redshift 0, that Daniel talked about, and many others also do. We bring that to close to redshift 1 so that all the galaxies are young. It's easier to resolve their star formation histories. And we combine the look-back approach with this archaeological approach. Okay, our sample is in the cosmos field. As I said, it's a very large allocation of VLT time, and we went out of our way to take very deep integrations. And as a result, we have these nice spectra with typical signature noise of 20 per angstrom at high spectral resolution. That is the stellar mass versus redshift distribution of the sample. This is where the knee of the stellar mass function is in these redshifts. So we really probe around L star, both below and above. The color coding is the completeness, and that just refers to the fraction of all galaxies in this volume in the cosmos field in this redshift range that we have observed. Of course, we start to be incomplete here, but since we understand the selection function very well, it's purely K-band selected. Even highly incomplete samples can be used to make general statements about the galaxy population. Okay, the third and final data release is coming up. I had hoped to finish that before this meeting, but as things go, that didn't happen in time. We decided it was better to do it right than to rush it and wrap it up now, but it's coming real soon. So this is what our spectra look like if you look at them all at once. These are all the spectra with measured stellar velocity dispersions and measured H gamma absorption line strength. H gamma is over here, just because it's sort of in the middle of our spectral coverage. The color coding is nothing else but ordering by H gamma absorption. So the strongest H gamma absorber has the bluest color, the weakest has the reddest color, and then there's these in between colors. Now, a couple of things you see here is in the old galaxies, we have strong D4000 breaks and these dozens of absorption features that we can use to model the spectra. But the key is that we see all those same features even in the bluest galaxies, in the individual spectra of the bluest galaxies. Right, and that's where the value of LEGA-C is, because it really spans the entire galaxy population regardless of type. It's purely K-band selected and blind to anything else. To appreciate the data quality a bit more, let's take a somewhat more detailed look at some of the individual spectra, I really like these post-starburst spectra just because they have such spectacularly strong Balmer absorption lines. Here's H delta, sorry, there's no labels, H delta, H gamma, here the Balmer break. So in black we have the spectrum, and in red we have the Conroy SPS model, a linear combination plus polynomials plus broadening by the velocity dispersion. That was all done by the PPXF code as published by Capellari in 2017. And it all fits very well, and all those wiggles you see here is real information. If you look at an older elliptical galaxy at redshift 0.7, there's now 2 star population models. So it fits in the theme we've been discussing so far. There's the Conroy SPS model, and here it's important to note that that's built with theoretical stellar templates. And you can see those spectra, those models in detail don't fit our spectra as well as this model that's based on empirical templates from the Miles library. The advantage of the Conroy, these theoretical templates have a very high spectral resolution that matches our spectral resolution better, so we still use it for the kinematics. But for stellar populations and emission line subtraction, etc., we use the empirical templates. Anyway, too much detail. This just goes to show that the high signal noise of these spectra help us constrain these very models, right? You need this data quality to do that. Why do this at redshift 0.7? Well, we don't, in the present day universe, we don't have 3 gig-year-old massive ellipticals with high metallicity, right? Those stellar populations don't really occur in nature in the present day universe, which is another good reason to go to larger look back time. So here's one of the bluest galaxies in the sample. We still see all the absorption features, even though they're weaker. And here it's very nicely illustrated how we separate the light from the ionized gas, the emission line light from ionized gas from the stellar population light. And that works thanks to the high spectral resolution. So that's a joint SPS and emission line fit, also done with PPXF. So I have this for thousands of galaxies. And of course, it's hard to summarize those data in one plot, but let me show how LEGA-C really changed the game. I'd have to go pretty far back in time to collect the data that had been taken in this redshift range 0.6 to 1 before, and only one study by Anna Galazzi, a pioneering study, went through the trouble to measure stellar population properties from the stellar spectra. There are open data points. They do have stellar velocity dispersion measurements, but these people, including myself, didn't care too much about stellar populations at the time, so we didn't bother to calibrate our spectra well enough to make that measurement possible. So here's the effective radius versus the stellar velocity dispersion, color-coded with H delta absorption. So young galaxies would be here, old here. So all in all, 62 galaxies before LEGA-C with stellar population and stellar velocity dispersion measurements. Now LEGA-C produces more than 3,000 of them, so that's a huge increase in sample size. And not only that, it also increases the parameter space. We'll take a more detailed look at that in a minute. So now we see these beautiful trends between the beautiful correlations between galaxy structure and mass and stellar populations, really for the first time at high redshift. So if you blink a couple of times, you see that what LEGA-C primarily does is, of course, increase the sample size by a large factor here, but it really expands parameter space in this direction towards the young galaxies. So if we now separate quiescent galaxies from star-forming galaxies with a color selection, and I don't want to go into details there, you see that one thing you notice that almost all quiescent galaxies have the same velocity dispersion, right, in a very narrow range of about 200 kilometers per second, plus minus not that much. There is range, the error bars are small, so there are large differences, of course, between 150 and 300, but the range is narrow. Generally, these quiescent galaxies are old. That kind of makes sense. Here you see a smattering of young galaxies. Those are the post-starbursts. On this side, things are a bit younger than here, so you see a very complex structure here. If you compare it with now we see that all these previous surveys were focused on those quiescent galaxies, right? And they lie in the same place, and there's very few data points here. Now this is where the star-forming galaxies lie, and then you do see this range from very young to intermediate. if you go from low dispersion to high dispersion, that's a very gradual trend in a different direction than for the Quiescent galaxies. It's all very interesting. This is just to show what the data set as a whole looks like. If you blink, you see how these two populations are really offset from each other, and there's some form of bimodality. Now, of course, these data are very inviting to do full spectral fits, not just for the kinematics, but also for the stellar populations. A few years ago, we made a first attempt to do this. It's limited in scope, but will improve in the future. But what we did was build linear combinations of FSPS templates with different ages. Those are the red lines. And we fit that to our spectra, the black lines. There's 6 examples here, 3 young galaxies and 3 old galaxies. And in the inset panels, you see the star formation histories. So star formation rate versus cosmic time. So the Big Bang was here. This old galaxy had most of the star formation in the first few gigi years. Then it took a break, and then there was a rejuvenation attempt. There was a separate paper about that topic. Most galaxies don't do that. Most Quiescent galaxies look like this. Anyway, you see that the contrast in the star formation histories between this group and that group. And if you sort that by stellar velocity dispersion, you see the following. So in blue and green, we have low velocity dispersion galaxies, and in orange and red, high velocity dispersion galaxies. We plot their average specific star formation rates over time, and we see that the high dispersion galaxies at the time of observation at redshift 1 have lower star formation rates than the past average. Thank you. 3 minutes. And the low dispersion galaxies actually have higher star formation rates. Now, on the one hand, this looks like the downsizing effect we see in the present day universe. On the other hand, if you were to make this plot in the local universe, all these lines would go from high to low, right? And here you see again the contrast at redshifts near 1. These L-star spirals, that's what we're talking about here, are in the middle of their main formation phase. Their current star formation activity is higher than their past average. Okay, in the final couple minutes, I want to spend a few words on spatially resolved kinematics. So far, we've talked about integrated measurements. Now, but we have a slit in this direction, spatial slit. Here's a HST image, and these are the spatial elements we have, and then this is the wavelength direction. We can extract the spectrum at each spatial position and repeat the velocity and velocity dispersion measurements at each spatial location. So you get a rotation curve for both the gas and the stars in blue and red, and a velocity dispersion curve here. Okay, so it's the first time we can do this stellar kinematic. It's the first time we can build stellar dynamical models for a large sample of galaxies at high redshift. And what we do is we combine the velocity dispersion and the velocity into a VRMS, and to that radial distribution we fit a gene's axisymmetric model. Okay, the ingredients in that model are the stellar mass-light ratio. We have an NFW halo. We fit for inclination and anisotropy as well as we can. It's basically marginalizing over the priors. And what we get is a mass and a velocity structure, a V over sigma. So the V over sigmas from those models we have for about 800 galaxies look as follows. The color coding is now Sersic index. So these are things with disk-like structures in blue and the more elliptical type structures in red. And we see that both independent of Sersic index, we see a very broad range in here shape. So this is projected shape, ellipticity, and here the projected V over sigma, inferred from the model. Now the low Sersic index galaxies, they rotate faster on average, but there are lots of red data points here, lots of concentrated elliptical-like galaxy profiles that actually show lots of rotation. Here there's a very prominent population of high Sersic index slowly rotating galaxies. Now this is a model value, so there's no reason really to talk about projected quantities, so we deproject it. And we learn a few things from that. One is that the model works well in the sense that phase-on disks, look at the blue data points here, have the same V over sigmas as the edge-on disks. So that means that there's no bias with inclination. That there's lots of high Sersic index galaxies here, completely mixed with the disky population. And this population of high surging in the galaxies here. I get the stop sign now from Claudia, so maybe somebody can ask me about this plot. Thank you for your attention.
Thank you, Arjen. I'm just taking the timer. Please, thank you for this interesting talk. Questions? I think Daniel Thomas has a question, then Michele Cappellari. Please go ahead, guys.
Yeah, thank you, Arjen. Brilliant stuff. Really amazing data quality at that redshift. I was curious about the specific star formation rate plot that you showed, where you have, so it makes a lot of sense what you said, but what puzzles me a bit is this strong bimodality. Wouldn't you really want to see some continuum between the as a function of sigma, rather than this very clear separation?
Yes, if you look at the individual star formation histories, there's no gap, right? This is a matter of binning. It's related to this plot where all the early types are sitting at the same dispersion. So they really start contributing to the population at about log sigma 2.2, and that's just at around 170. So at this orange line, the early type population kicks in. So if you would make finer velocity dispersion bins, you would see that filling up. And again, the individual star formation histories, to the extent that the individual ones are trustworthy, they really fill up into the entire parameter space. It's not that our fits choose it's either there or there.
Mm-hmm.
Right? You might also get an impression here, it's either old or young, but it's kind of the way these three examples were chosen to contrast with these three.
Thank you.
Okay, thank you. Michele, next.
Arjen, I really like what you're doing at those redshift with LEGA-C, and I would have a number of questions, but especially on the dynamical part, you had to cut short on the very interesting result you were showing. So can you comment on that slide that you couldn't comment at all?
Thank you, Michele.
I'm going to talk about this. Feel free to show the slide, Arjen. We have actually time during the discussion. Yes.
Yeah. So I will talk about this for the next 20 minutes. So here's now the deprojected view over sigma again. So that's the same as in, this plot. And here's the enclosed stellar mass within the effective radius from the dynamical model. Here for Quiescent Galaxies, we'll get the star forming galaxies here. So one thing you notice here is that there's a huge range, right? It's at this mass of 10 to 11th, you have rotationally supported galaxies, you have galaxies without rotation. Only at the very high mass end, you seem to be dominated by slow rotators already at this redshift. The star forming galaxies kind of show the opposite. Also a very broad range, right? The distribution is different, right? The most star forming galaxies are up here and under tail here, and here it's sort of more even. But here, if you go to the highest masses, there's exceptions, but you tend to find the most rotationally supported galaxies at the high mass end here, and here the least rotationally supported ones. Okay, now another interesting aspect here is the color coding. That's the velocity, the deprojected velocity at RE of the galaxy. You might expect, you see a lot of dark blue here, so these galaxies rotate fast at RE, but the fastest rotators are actually over here. These are the darkest blue. Mm-hmm. So maybe that's counterintuitive to the fastest rotating galaxies are actually quiescent.